Okay, good afternoon, class. Let's start our lecture. Okay, so we're going to continue today, and we have a new topic. Okay. So the new topic here is it's on surface integral. That projector seems to be flashing here. Yeah. Okay. So this is basically a new integral we're looking at today. And before we look at the surface integral, I'm going to introduce a concept, which actually is not a new concept. It's the concept called flux. Okay. I think in your Applied Science 178, and you probably actually covered or learned a little bit of what flux is. Okay, so in a very simple language, okay, flux is basically it's amount of something passing through a surface in unit time. Okay. So this is the very simple language description of what a flux is. Okay. So the keywords here is it's amount of something passing through a surface in unit amount of a time. Okay. And this something at here, right? Meaning could be anything. It could be as invisible as the electrical field, or it could be as tangible as something falling through the sky. Okay, so I actually sometimes I use imagine there are bananas falling through the sky. You know, that's something, right? And if you have a big bowl of surface, okay, you want to catch as much as that you can. So that's basically amount of flux, right, coming through that surface in unit amount of time. Okay. Now in engineering, there is a very important concept called transport flux. Okay. So this is a more related to transport phenomena. So for example, in your third year you will learn basically heat transfer. And there's also a concept called mass transfer. Okay. So in this area here, you also have this concept of basically flux or fluid dynamics that are similar. So in this case, the flux, okay, is defined as, so here is the wording here, so rate of a flow of a property, so rate of flow of a property per unit area. Okay, so rate of flow of a property per unit. So it's something, there's a fluid or it's a heat or it's a mass. There's a rate of flow of this property, right? So how much basically, let's for example, distance travels per second, that's rate. per unit area, basically going through a unit area, right? A small area, something like that. So that would be the definition of flux in this area here. Now, if you want to write down the dimension, right? The dimension would be, let's see, depends on what quantity it is or what property it is. So there's a certain amount of quantity, and then the time inverse. So this is basically the rate, right? This is the rate of flow of this property. And then you time the area inverse. So that's basically per unit area. So that would be the dimension for this transport flux. Okay. Yeah. So if you are, for example, if you're talking about heat transfer. Okay. So heat transfer, you see the rate of heat flow across a unit area. So in general, we have a unit, something like a J meter negatives, okay, and seconds to the power -1. So that's basically, right, same the unit here, quantity, right, joule here. There's time inverse and area inverse. Okay, and you can similarly have a mass flux, okay, or heat. This is basically heat flux. So I should write heat flux here. Okay, so that's transport flux. Okay. Now, in this course, right, we're going to talk about flux, and we're going to calculate the flux, okay, of a certain quantity, rate of this quantity through a certain area. So what we do is, okay, we basically going to describe all the calculation of flux, okay, using the so-called, this is the topic of today's surface integral. Okay, so this is the topic we're going to do here. We're going to calculate our flux using this concept here, okay, called surface integral here. Okay, yeah. So before I give you the formula, right? Before I give you the formula or even derive the formula, so let's just think about in general, right? What does this flux using surface integral means? Okay, so I'm not sure if you guys watch cartoons or not, and this is actually not a really new one. You know, you watch this. This is a cloudy with a chance of meatballs. Okay, and I watched it quite a few times. So let's say you have meatballs falling through the skies. Okay, it's just like Christmas comes early. So you trying to hold a bowl at here, trying to catch as much as possible, right? So this meatball is this quantity, okay? This is property, okay? There's the rate of flow here. So now think about it, right? So you only have this much at here. So the question is, how could you catch as much as possible, right? What condition will give you the maximum quantity that you can catch, right? Think about it. How would you catch as much as possible? So there's something falling down here, right? I guess if you want to catch as much as possible, first of all, I want a bigger bowl, isn't it, right? As big as possible. Well, second of all, you want to orient your bowl to what? To be perpendicular to the falling of these meatballs, right? Okay, and so basically, the meatballs could be falling down this way. That you probably can't change, right? Or you could probably falling down this way here, okay? And you have a surface that is here trying to catch as much as possible, okay? So basically, I have another one here to show you what matters in terms of the passing this quantity through that surface. It matters in a number of ways. First of all, you know, it matters with what? The density of this quantity. Okay, so you probably have a faster flow or a slower flow, or you have a much more density type of a field. Right. So apparently this one will have a much more quantity passing through the same surface here. And second of all, the orientation of the surface matters quite a bit. Right. If it's a flat with, you know, if a flat in terms of with respect to the original field, then you don't catch anything. But if it's perpendicular, then you catch all of them, right? And also the size of the surface also matters. If it's a smaller size, definitely there's not much going through it. But if a bigger bigger size surface, and you catch much. So that gives you a sort of idea. If I wanted to calculate that amount of stuff passing through the surface, and we need to catch this, basically the three information set here. The formula we presented here we'll have to catch these things in here. So now you actually mentioned one thing in here. Basically you said, okay, so you really want to orient your surface to be perpendicular, right? To be perpendicular to the direction of the falling down of the fields that are here. Okay, but often in time, you know, your surface you can't change, and the field you cannot change either. So everything is basically constrained there. So then there has to be some sort of relationship to describe what we just said there. For example, if I have a surface here, this is given, so you can't change anymore. This is in the space. This is the surface. So we can always indicate at each location of the surface using the so-called normal vector. So at every point of the surface, you will have a normal vector indicating this surface at here. Okay? Yeah. So if I make another drawing at here, okay? So basically, for example, if you have a surface, okay? If I pick just one small location of the surface at here, okay, then there is definitely a normal direction n hat at this location. Now you may have maybe a whole lot of stuff passing through this surface. Okay, yeah. So maybe this is your quantity flow through this surface at here. And to describe the flow of this quantity, we can use a so-called vector field, which we learned, right? We can use a vector field to describe basically the flow of this quantity. So at this location here, I can use an F vector at here, right, to describe the flow of that quantity through this point at here. Okay? Yeah. So now you see, right at this point, you have two information. One is the normal direction for the surface, and the other is what? Is the direction, the flow of this property, of the quantity. Okay? So when it comes to what would be the actual effective flow, the quantity flow through the surface, it's not this F, not just this F, because it's not perpendicular, or it's not in the same direction as the n hat. So really, what really flows through the surface at that point is what? It's the projection of this F in which direction? In hat direction, right? So at this point, it's the projection of this quantity in the direction of this n hat. So that's that much going through it, right? Yeah. So this is actually an idea give us now. In order to calculate the double integral the flux at here, so let me use this concept here again to basically derive the formula for this surface integral here. Okay. So now let's consider, instead of just a point, let's consider maybe an infinitesimal small area. Okay, so this is a very small area, delta A, not really infinitesimal, but a very small area. Okay, if it's very small, then we can consider it's a even the quantity passing through this field is even, so there's no change, it's all constant. So the F here is all constant across everywhere of this small area. And we can consider it's a flat area, so there is just one single normal direction n hat for this small area. Okay, yeah. So now you can literally say, okay, so what would be the volume of this property of this quantity passing through this delta A in unit time, right? In unit time. So the way you calculate the volume basically is, okay, so I use the base area and then times the actual height, right? The height. So the height here is not this one. The height is what? The height here is the projection of this in the direction of n hat. We learned that in the first lecture, basically, for a volume of parallelogram. So at here, essentially, you get the volume, okay, which equal to the base area, okay, and then times the height, which is F dot then n hat. So that's the effective portion of the quantity, right? That's the effective portion of the quantity passing through that area here. So this is your volume. The volume in here basically is the flux. Okay, it's a delta flux. Okay. So that's a little bit of flux passing through this delta A at here, which is this much. Okay, this much. Okay. Now, but we're talking about is what? We're talking about is the total flux across the whole surface at here. So all you need to do is you just have to integrate both sides, okay, to get the total flux. Okay, to get a total flux. So now the integration at here basically give you the flux equal to over here. Okay. Now instead of just a single integral, it's actually a double integral. The reason is because I'll explain this after I write it down here. So this integral here, so this f dot n hat and then dA at here. So this is your basically surface integral for flux. Okay. Or the wording I said flux in surface integral. Okay. So that's the formula. And I'll show you how to calculate this one here, as going to show you, as you will see that even though this is a new concept, but the computation of this one is actually no difference, because it's basically it's going to be a double integral at here. Okay? Yeah. Now, why is it a double integral, right? Because we're talking about the surface, so you're trying to integrate through this given surface at here. If you recall that when we're integrating triple integral, it's integrated through a solid region D, right? So basically you have a x, y, z. You sweep in 3 directions to basically cover the whole, sweep through the whole region D. But in this case, you're integrating over a surface at here. So technically speaking, you don't need 3 variables anymore. You only need 2 variables in order to sweep through this surface at here. So that's why it's a double integral. Okay? Yeah. So this whole idea here is integrating over the surface S. Integrate what? Integrate this quantity. Okay? Yeah. Then you get the total flux. Right. Okay. Now the rest of the work, okay, is basically it seems to be a lot, but actually I'm going to break it down to individual sections, and each one of them as it pans out will actually turn out to be really nothing new. It's just a repeat of the double integrals as we learned before. Okay? Yeah. Now before we move on here, there's another thing that I guess I need to cover before we move on. Okay? We need to cover another concept called orientation of a surface. Okay, orientation surface. Now this orientation of the surface, it's different from what I just described, like you move your surface like this. Okay, orientation of the surface basically it's the normal vector n hat, okay, to the surface. Okay, so this n hat, it has 2 directions. So for example, if you have a surface at here, so technically speaking, you can have an n hat pointing this direction, or you can have an n hat pointing the other direction, right? Yeah. So technically speaking, you can have 2 directions. Now, this is an open surface at here, right? This open surface. The direction of the n hat literally determines the orientation of the surface. Okay. So when you see the surface pointing that way, this is one direction, and when in this way, it is another direction here. But it's more used for a closed surface. Okay, if a surface is closed. Okay. If a surface is closed, basically means if you have a sphere, for example, right? That's a closed surface. Or if you have a half sphere at the bottom is a xy plane, for example, that's also a closed surface, right? So it consists of 2 surfaces. Okay. Now, if they're closed, okay, then here we have a convention. Then we say that the outward flux, okay, is considered positive. Okay, consider positive. So basically, you place your surface inside a vector field, which represents certain moving of certain quantity. And if I ask you, what's the outward flux, right, through this surface? So when the question is asking like that, then when you calculate the surface, the n hat should be pegged to as which direction, right? For example, if you have a surface at here, so you have an n hat pointing this way, you have an n hat pointing this way, right? Let's call this n1, n2. If you are required to calculate outward flux, then you need to peg this n hat. Okay? Yeah, that's basically the orientation of the surface means. Right? So pegging this n hat appropriately. I mean, you only have two choices basically. Okay? If you pick a wrong n hat, then your results just supposed to be a negative difference from the other direction, right? Yeah. But technically, it's completely different. Okay, it's wrong. Yeah. So that's basically what orientation is at here. Okay, you can see outward n hat, okay, is positive. Okay, it's another way of saying this. Okay. All right. So now come to the evaluation of this surface integral. Okay, so let's look at evaluation of surface integral. And as I explained, I mean, you don't need 3 variables to evaluate this surface integral. You need 2 variables to evaluate surface integral. So we're going to look at some special cases at here. Actually, at the end, we're going to look at maybe a more general case, right? So let's look at each one of the cases at here. For the first case, let's look at a spherical surface. More precisely, it's a spherical surface centered at the origin. Okay. So if you have a surface which is like this, then what does this surface integral become? Okay, that's basically the idea. And then next we'll look at cylindrical surface, a plane parallel to xy, for example, right? Yeah, and then we'll end up with a more general surface at the end. Okay, so that's the first case, spherical surface. All right, so this is the illustration at here. It actually took me a while to draw this thing here. Here is a spherical surface, right? And what we're trying to do at here is, for example, we're trying to integrate over the whole surface. Okay. Integrating over the whole surface basically means you're trying to scan through every locations on the surface. That's basically what it means, right? Yeah, just like a triple integral or double integral scanning through a region. So here's one we do is, so in order to scan through this, we can pick a small area first, okay, and then use this one little area and you scan through the rest of the area. All right. So the idea is basically, you see, this is the formula, right? This is the formula. Okay. Then what is dA? So basically, this is the idea. What does dA equal to? And here is n hat, and we also want to figure out what n hat is, right? So that's the point. If you can figure out this and that, okay, so then everything will be fine. Okay, yeah. Okay, now let's look at the dA first. So this is how we section this surface, okay, into small area delta A, very much like sectioning xy plane using x coordinate and y coordinates to draw 2 lines. Then you can basically get a rectangle, right? So here we draw something in a direction of the theta direction and also the phi direction, so we can literally come up with a delta A small area. So the delta A small area, okay, this is a sphere with a radius of a. Okay, so the a at here is the radius. Now this is a constant. Okay, so this is a constant. Basically, we're talking about a spherical surface with a constant radius a. Okay, constant radius a. Now, if you look at the way we section out this dA at here, you can easily obtain an expression for the dA, which is equal to a times square sine phi times d phi d theta. Okay, so the theta phi is part of the, remember what part of what coordinate system? Spherical coordinates, right? So now you look at this dA at here. If you jog your mind back to the formula for triple integral in spherical coordinates, this is very similar, isn't it? This is very similar. In spherical coordinates, you have a dV, which is a volume, right? Volume equal to what? Rho square sine phi, and then d rho d phi d theta, isn't it? Right? Yeah. Now, but that's scanning through the whole solid region, right? So you have to go through this rho direction. But here you only scan through this surface. So guess what? The rho, instead of a variable, becomes this a squared. So you don't have the d rho anymore, and you get the dA at here. So this is basically how the dA is derived here. Okay? Yeah. So that's your dA. So we're going to replace this dA into this location. Okay? If we have this under this first case spherical surface at here. All right. Good. So let me write down the dA again at here. Okay. So a sine phi and d phi d theta. So that's your dA. So next, let's look at what is this n hat. Okay, what does the n hat equal to? First of all, you have to understand what is the n hat. The n hat is what vector is this? Normal vector. Okay, so this is the normal vector to the spherical surface at here. Okay, so you do have two directions, right? You could have a direction pointing outwards or pointing inwards. Now, I think we learned, if you recall, when we learn circle, right? When we learn circle, for a circle here, what will be a normal vector to the circle? What will be a normal vector to the circle? Normal vector circle means that if you starting from origin, you draw any vectors out of this origin here, that vector is what? Normal to the circle, right? To the circle, the curve of the circle. Now, back to the spherical surface, then what will be a normal vector? Forget about unit vector. This is a unit vector, right? What will be, first of all, let's see. What will be a normal vector to the spherical surface then? You do what? You pick any point on the surface. You connect that point, okay, with origin here. Now, that is a normal vector to the surface, right? Yeah. So any reading lines, out of the origin is normal to this spherical surface, right? Okay. So let's say this is a P at here. Okay. So P has the coordinates of x, y, z. So that's basically means OP. Okay. OP is a vector perpendicular to the surface. Okay, to the surface. But what we need is a unit normal vector. Okay? A unit perpendicular vector to the surface. So guess what do? Just normalize it, right? You can just normalize it. Okay? So now you see we can putting things together now. OP represent a vector x, y, z. Okay? X, y, z. If the coordinates for the P is x, y, z, then OP is x, y, z. And the bottom here is the length of OP. And what's the length of OP? Exactly, right? That's your norm here. Now, I will put a positive and negative here because for unit normal vector, I could have either directions, right? Outward or inward. So I'll put a positive and negative here. But when we calculate, when we evaluate a certain question, and you always have to select a positive sign or negative sign based on the requirement of the question. Okay. There we go. So that's basically your dA, and that's basically your n hat at here, right? Okay. Now you see the way we have a dA and n hat. It's not very consistent then, right? Because dA is in which variable set of variable? It's in the spherical, but then the n hat is still in the Cartesian coordinates, right? Yeah. So we want it to be consistent. Consistent basically means all in the same variable. Now this is a spherical surface, so chances are what set of variable you want to use? Spherical, right? So this is basically what we want to replace our x, y, z with the spherical coordinates. Okay, yeah. But this x, y, z, you still have to be very careful. This x, y, z is not an arbitrary x, y, z all over the space, right? This is x, y, z located where? Located on the surface, on this spherical surface here, which has a radius of a. So the x that is here, if you recall, that used to be rho sine phi cosine theta, isn't it, right? That's the connection between Cartesian and spherical. But we're talking about the specifically sphere with a radius of a. So this is not the rho at here. It should be what? It should be the a at here. Okay, so the radius of the circle. So that's your x, and y here would be a times sine phi sine theta, and z equal to a times cosine phi. Okay, so this is how we're going to replace our x, y, z with these three expressions. So finally, we're ready to putting everything together into the formula for the spherical coordinate for the surface integral. Okay, then so I'm gonna before we put together here, there's one more piece of puzzle. So here's your vector field. Here's a quantity, right? This is the quantity we're talking about here. Yeah, right. There's some sort of anyway. So here we also have to do some replacement for this vector field that is here. So that x, we're going to replace it with a sine phi cosine theta. This y will replace with this a sine phi sine theta, and the z with a cosine phi. Okay, so that's another step of a replacement, okay, of variables. Okay. Now you're truly ready to put everything together. So your surface integral, which is f dot n hat dA. Okay, what does it equal to now? So it equal to, okay, double integral, and here this is your f function, and here, okay, this is your f function. So the f function basically becomes a theta and a phi function. Once you replace everything, okay, it's basically become a theta and phi function, right? Yeah. Now f here, maybe a little more specific here, okay? So f here, you technically have a m n p. Okay, so you have three components, right? It's a vector, so you have a m n p there. Okay, so we technically speaking, we have m n p, okay, for this f function, and then dot the n hat, and n hat, as we just derived, is 1 over a, okay, x, y, z. Okay, so let's leave the x, y, z for now. Okay, then we can do the replacement at the end. Okay, and dA is a square sine phi d phi d theta. Okay, yeah. Okay. Okay. So this will be the formula here. I mean, you can literally keep writing. Okay, replace this x, y, z. Okay, here with the three expressions. Okay. Same thing, the m and p, the x, y, z within the m and p should be replaced like this too. Okay. So you can literally just go on here. We don't need to derive a more formal formula. There's no point to derive a more formal formula here. Each question will have a different m and p, so we can actually do the replacement okay, for each individual question. But you have to bear in mind that you're not going to carry this x, y, z through the question here, right? You're going to replace the x, y, z with these three expressions. Okay, yeah. But then, of course, the question here is, okay, so I have a d phi, d theta. Then what will be the basically the integral limits now for phi and theta, right? Yeah. Now, as a matter of fact, this is actually up to this stage. There won't be anything new anymore. The process of finding the limits of phi and theta will be no difference from the process when you used in evaluating the triple integral. Okay? Yeah. So I'll show you through an example, and you'll see what I mean here. Okay? Yeah. So let's take a look at the example here. So let's say I have a vector field F, okay, 0, 0, Z. So that's basically, if you're trying to visualize in your head this vector field. So this vector field always pointing in the z-axis direction, okay? And as you're moving more and more away from the 0 point origin point, so z is become a bigger value, so the vector will become bigger quantity, right? Bigger magnitude. Okay. So suppose that the surface given it here, okay, is the spherical surface. It's a whole spherical surface. It's an enclosed spherical surface with a radius of a centered at the origin. Okay. And I want to calculate what will be the outward flux, okay, at here. Okay, what will be the outward flux? Okay, so this is a simple exercise of putting things together, right? There's no trick at all here. Okay. So our flux basically means we are going to pick n hat appropriately. But let me write down the formula for the surface integral again. So that's a surface integral. N hat. Okay, so let's pick the n hat first. Okay. Now the spherical surface. So n hat, we're going to use the positive one because we're talking about our flux, and it's 1 over a x, y, z. Okay, 1 over a x, y, z. Okay, so within this surface integral calculation, you see here you have a f dot n hat. So you have f dot n hat. So I'm going to try to calculate this f dot n hat first. Okay, just break down the calculation a little bit before putting everything together. So f is 0, 0, z dot 1 over a x, y, z. Okay. That's the dot product. So this is good. So it's just 0, 0 here. So 0 times x plus 0 times y, and then plus z times 1 over a z. We get 1 over a z squared. Okay. That's f dot n hat. Okay, so now I think I'm ready to putting everything into this surface integral now. So let's put this surface integral. So f dot n hat is 1 over a z squared. dA is a squared sine phi d phi d theta. Okay. Yeah. And this is your surface integral over this asset here. Now we're going to replace the z. We're going to replace every x, y, z with the spherical coordinates. So replacing the z with which quantity? With a times cosine phi. So that's your z. Here's another a squared sine phi still there. Okay, so that's the surface integral. Okay. So good. So up to here, you got everything consistently in the spherical coordinates now. And the last step is to find the limits for the phi and theta, right? Limits for the phi and theta. So to find the limits for the phi and the theta, okay, going back to this, let's say, to the sphere here, okay, going back to the sphere. How do I find the phi and the theta? Now, if you recall that the process finding phi and theta in triple integral, So how do we find theta? What do? We basically draw a reading line first, right? But the first step is for rho. And the second step is to sweep this reading line starting from the z-axis and then sweep all the way through this surface. So, but you don't sweep too much, right? You only sweep from maximum is pi. So minimum is 0. So in this case here, you see you find the edge, one edge over here, one edge over here. So that corresponding phi min, phi max will be, in this case, is 0 to pi, right? So 0 to pi. So this sweep right here, essentially, it's like generating a cross-section, half cross-section, a half circle cross-section, circular cross-section. Okay? So from up, sweep down here, okay, you got a 0 to pi. So that's your phi limits. Okay, that's your phi limits. And then the theta limits, right? The theta limits is you will look at basically the shadow of this surface, which is the circle. So the theta is you sweep this reading line across the whole shadow. Or in other words, you sweep this whole half circular cross section, right, across the whole spherical surface, which is 0 to 2 pi, in order to recreate this spherical surface, right? Yeah. So that's the second portion for the theta will be 0 to 2 pi. Okay. So this is no difference from the way you find the limits for phi and theta when you do triple integrals, right? Triple integrals. Now, the rest of the work is just integral now. We can let's carry this a little bit here. So I find sometimes people can make a mistake, especially during exam setting, either forget a square here or miss the a or here and there, right? So we've got to be careful sometimes. So there's a square, another a square, get rid of one a, so you get a cube. So I can take the a cube out of it, and then inside here is cosine phi squared sine phi d phi d theta. Okay. And I think by now you should be pretty confident when you look at this integral here, and that should require you a simple a substitution, right? Yeah. Then you should be able to finish this. And typically, what I do, I just this d sine theta it's a negative d cosine theta. So you got the same cosine phi here, and then you can treat it as like a x squared dx, right? And then you can calculate. Okay, yeah. So this should be a pretty easy one. So you should get 4 over 3 pi. Actually, did I get this? Yes. You should get a 4 over 3 pi a cube for this calculation. Okay. Any questions? Right? Yeah. So you see, as I promised, even though this is a new concept, but when it comes to the interpretation, when it comes to the evaluation, it's actually nothing new, right? Actually nothing new. So that's the first special case, when you have a spherical surface centered at the origin. Okay. So let's look at another special case, number 2, which is a planar surface. Okay. I'll illustrate what a planar surface is. Okay. So for example, let's say we are given a surface like this. Okay. So here's a surface. And this surface says z equal to a. Now that's what planar surface means right here. It's a surface parallel to the xy plane. Okay, and then we can easily extend that to a surface parallel to xz or surface parallel to the yz. Okay. So you place this surface inside a certain vector field, for example, or the vector field basically represent the flow of a certain quantity, right? Okay. Then we're saying, okay, so then what's the flux, okay, going through this surface here? And of course, you can either see the flux going upward flux or the flux going down, right? So because for this surface, you can have n hat this way, or you could have n hat this way. Okay, so either way is a normal vector to this n hat. Okay, so now you can literally write it down now. So okay, so n hat has two directions. What are they? They're basically positive and negative. What? For the n hat for this planar surface. What vector? Huh? K. Yeah, it's k hat, right? So that's your unit vector for the n hat here, which is basically k hat in the z-axis. Okay, and you can write it either as 0, 0, 1. Okay, for the n hat. Okay, and then dA, right? The small area. You take a infinitesimal small area. How do we do that? In this case here, because this is a planar surface, so we actually will use the Cartesian coordinate. So you can construct a very small area at here. Let's call it delta A equal to delta X delta Y. So the dA at here basically is equal to dx dy. Okay. So that will be your dA. Okay. So now you can put things together. Okay. So putting things together basically means here is your vector field MNP, and n hat is positive, negative, 0, 0, 1. Okay. So that's your n hat, and dA is dx dy. So you can literally replace a lot of things now, but because 0 times m is 0, 0 times m is 0, so then you can just get, let's put a positive here, so p at here, right? That's just the p function, okay? P function. And then dx dy, okay? Dx dy. Now remember, here you have to be very careful. This is a vector field F. This is a 3D vector fields, right? 3D vector fields. So each one of the component is a function of x, y, z. Okay, it's a function x, y, z. But now you are talking about this function, okay, or vector function here. It's not anywhere else. It's a specific location where it's the location at this z equal to a. So what do I do with x, y? I keep it, but what do I do with the z? You replace the z with a. Okay, yeah. So that's basically the double integral here. So now the rest of the work is, let's find the limits for x and y based on the given planar surface. Okay, maybe it's just a rectangle, or maybe it's something else, but you will find, yes. A is the plane location, z equal to a. Right, so that's where you're doing the integrals. Okay. You're integrating through this z equal to a. Maybe it's bounded, okay, by some boundaries. Okay. A will be, you can call this is basically now it's some kind of a region R now, right? Some kind of region R. So it depends on the question. Okay? Yeah. Is that clear? Okay. So now I want you to expand this from here very similarly. Okay. Now if we're talking about a slightly different planar surface, let's say if the planar surface is x equal to a. Okay, that's a b here. Let's use a b. Let's say if this planar surface is x equal to b. So x equal to b basically means it's a plane parallel to which to which one? So when x equal to b, so you draw a constant line here. So that's a plane parallel to which plane? To the yz, right? So if this is the case, then your n hat, okay, you can literally just modify it very easily. So the n hat will be positive, negative, I hat. And your dA will be dy and dz. Okay. So that will be the difference from the z equal to a. Similarly, if you have a y equal to c, then this will be positive, negative j hat, and then dA will be dx dz, okay, or dz dx in the math. Okay. So that's the second special case. Okay. This is actually should be the easiest case in my mind. I think, you know, really there's nothing tricky here. At the end of the computation, it's basically a double integral through a certain region, right? Through region R in there. Okay. Yeah. Any questions? Good. Okay. So maybe let's take a look at the very quick example at here. Okay. Yeah. -1, 2, 3. So here's a surface z equal to 1, and then x is between 0 and 2, and y is between 0 and 3. Okay, so if you draw this out, basically x is between 0 and 2, y is 0 and 3, and z is 1. So it's a plane. Right? This is a plane. A rectangle. It's a patch, right? It's a rectangle patch, okay, parallel to the xy plane here. So that's your surface. Okay, that's your surface. And here is your vector field. And this vector field, in this case, it's actually very simple field. It's a constant field. -1, 2, 3. You know what? Maybe let me just give you a. Let's say this is a z here, right? Let's just say this is a z. So let's carry this. Let's call it. Let's say I want to calculate upward flux. Okay. So how much flux going upward? So what do? We start from. The formula for the surface integral, okay, and let's put down all the known quantities. And f is -1, 2, z, and then, well, I guess one thing before we move on here, what do I do with the z again? Change the z to what? To 1, right? Okay, and then dot n hat, because I'm talking about upward. So I'm going to talking about 0, 0, 1 in it here, and that's dx dy. Okay. And then dx dy depends on the boundary for this small region R here. And apparently x is 0 to 2 and y is 0 to 3. So you can, if they're not a regular square or rectangle, if they're bounded by certain lines or here and there, you know, you use the same basically a strategy, right, to find the x and y limits as you're doing for a double integral. Okay. Okay, so you can calculate this one here. I think that should be pretty easy. It's -1 and answer 0, so there's 1 here, so dx dy, right? Dx dy. Okay. Okay. So you actually don't need to calculate anything at all, because what this one actually says is what? You get the area for this small region, which is one side times the other side, equal to 6. Okay. Is that good? Okay. So that's the second special case when you have a planar surface, right? That's also a very easy one. So let's look at the third special case. Cylindrical surface. Okay. Cylindrical surface centered around z-axis. That's an interesting class. So, yeah. Centered around the z-axis, okay, with radius of a. Okay, yeah. So I'll draw this out because we call it special case. That's why it's not a cylinder, at anywhere else, right? So we're talking about cylinder basically centered around the z-axis. So far, don't worry about the upper or lower limits for the cylinder, but it's just a cylinder, could be extending anywhere up and down somewhere with the limits, right? And the radius of the cylinder here, as I said, it's a and here. So that's the special surface, right? So this is the surface we're talking about here. And let's say we place that MNP, place that surface inside a vector field, okay, F, and we wanted to calculate the flux of this vector field, right? Either outward of this cylindrical surface or inwards or into this cylindrical surface. But typically we'll probably just say outward flux, right? Yeah. Okay, so we'll go through the same process because we have the formula. We just need to figure out. So I ran a battery. Just give me a sec. Okay, so we have the what do we have? Oh, we have the formula, right? We have the formula here. Okay. So we just need to figure out what the n hat is and what the dA is, right? So that's basically what we need to figure out here. Okay. Yeah. So to figure out, first of all, let's look at the dA here. Okay, the dA. Now to find the dA, okay. So let me bring my pictures into my notes. Alright, so here's what we're going to figure out the dA here. So we're going to section this cylindrical surface into many small pieces by basically drawing lines in the theta direction and also in the z direction. So it's like this. Okay. So you draw lines in the z direction and you also draw the lines in the theta direction, r direction. Okay, yeah. So then you would be able to come up with a small area, a delta A at here, right? Small area delta A. But one thing you got to bear in mind is this is different from the triple integral using cylindrical coordinates. Because why? Because currently it's a cylindrical surface, so the radius of the surface is always a constant, right? It's always a constant, and the constant is a at here. But cylindrical coordinate, triple integral cylindrical, you have the r, right? The r here could be a time not a time, it could be a variable here from 0 to somewhere else, right? So this here, your r is a constant, huh? So basically your r is constant, r equal to a here. And the small delta a at here, the small area, you can treat it as if it's a rectangular area. And that rectangular area basically is equal to a times dz times d theta. Okay? So this is a here. So a times delta theta give you the top portion, and then here is your delta z. So you get a times, basically it's a, if you write it this way, a times d theta times dz give you the rectangular area. And I can write it as a dz d theta. Okay, so that's your a here, delta a. So basically now you see, for the surface integral, in this case, we're going to take the z and the theta as the two variables to finish this scanning through the surface at here, right? Yeah. And n hat, right? N hat is a vector again. It's a vector normal to the cylindrical surface. Okay, cylindrical surface. So now if I look at it from the top, what do I see? We see a circle, isn't it? Right? Yeah. As I mentioned, what will be a vector perpendicular to the circle? You draw a vector out of this origin, and that's a normal vector to this circle here, right? Yeah. But this is a cylinder, right? This is cylindrical surface at here. So if I want a normal vector in the xy plane, that's fine. So this is n in here. So that one will go through this to the origin. But what about location, let's say somewhere here, right? So it will be very much the similar. So you have n in here. All you need to do is, right, just extend the n to the z-axis, which this one here is actually parallel to this one, right? So that'll make it a normal vector to the cylindrical surface. Okay. So essentially, your n hat, okay, if this is a parallel to this, the vector is always free. So actually, there's no difference, right? No difference. So the n hat here is just a vector. You can extract the vector from here. Okay. Yeah. And that vector, let's say if I pick a point inside the xy plane, if I pick a point of xy at here, but I'll put a 0, basically still considering 3D at here, okay, then the n hat will be OP divided by OP norm, okay, and this is xy0, and then divided by the length of OP. But our OP at here, this is a P point at which location? At anywhere on the boundary of this circle here. So the OP length is the radius of the cylinder, which is A. So that's your n hat, which is 1 over A. So I should have a positive and negative here because it could be pointing inward or pointing outwards, right? So that's your n hat, positive and negative A at here. There you go. So you got your delta A. Okay, I should say this is dA here now. So you got your dA, you got your n hat, okay, and there is a little bit inconsistency here because we have a z theta, but then the n here you have x and a y. So what do we do with x? So we use the polar coordinates or cylindrical coordinates, but we're talking about the points on the cylindrical surface. So a here, x equal to a times cosine theta, and y equal to a times sine theta. Okay, and z, no change, it's still the z, right? So that's the replacement. Okay. There you go. So you have basically all you need is this 3 lines of information here. You will have this in your formula sheet. Okay, so formula sheet is uploaded for everything I have written so far for the surface integral. You will have that as a collection in the formula sheet. Okay, so now I'm ready to put things together. We have f dot n hat dA, and f is mnp. So you have a 3 component for the vector f, and n at here is 1 over a x y 0, and dA at here is a dz d theta. Okay. So that's the formula, right? That's the formula. You don't really need to keep writing this one here, but I think if I give you the formula, this will be the formula. Okay, plus this. Okay, so you basically will substitute your x, y here. Okay, and also m and p is a function of x, y, z, and you do the similar substitution. The limits for z and theta, same way as we find the limits for z and theta when you're using cylindrical coordinates, right, in triple integral. Okay, so that's the formula for the special surface, cylindrical type of surface. Okay, let's look at an example, and just basically plugging a specific example here for this formula. Okay. Say that we have a vector field x, z, negative y, and the surface is x squared plus y squared equal to 1, okay, between z equal to 0 and z equal to 1. So you have a vector field, you have a surface, and obviously this is a cylindrical surface. And we're going to calculate this flux. Okay, let's calculate the outward flux. Okay, let's calculate outward flux. Yes?
So outward flux, inward flux, is the total flux 0? The flux across the full surface,
no. Oh, you mean when you add outward and inward together? Yeah, when you add them together, it will be 0. But because they are going to be just basically a difference, right? Yeah. But later we'll learn another one here, the Stokes theorem, I think, divergence theorem. So there will be a different concept. Yeah. Okay. Good. So let's look at the outward flux for this one here. So if it's outward flux, basically means we're gonna take the positive n hat for this cylinder. If you wanted to sketch this cylinder here, and it will be right starting from z equal to 0 and up to z equal to 1. So this is 1 in here, and the radius of the bottom circle is also 1. So that's your cylinder. Okay, it's your cylinder here. Yeah. Okay. Actually, I should probably come back to your Antonia's question in here. Now, you mentioned a closed surface, right? But in this question here, this is not a closed surface. We're only talking about flux out of the side of this cylindrical surface, right? Now, technically speaking, if I give you a question saying, can you calculate the outward flux for a surface that consists of the cylindrical surface plus what? Plus the bottom of z equal to 0 and the top z equal to 1. So basically, with the bottom and the top lead, right, together, then you will have what? An enclosed surface, right? Okay. Now, if that's the question, that's the surface, and if you're required to calculate outward flux, guess what would you do? Not zero. What would you do? First of all, let's just think of what would you do, right? First of all, how many pieces surface for the one that I just mentioned? 3, right? Okay. And have we just covered all the 3? We just did, right? There's one cylindrical surface, and the top bottom one. What type? The case. It's the case number 2, right? Planar. So when you're let's see, when you're calculating, I'm jumping ahead a little bit now. Let's say this is S1 for the cylindrical, and this is S2, and this is S3 at the bottom here. All right. So when you calculate the outward flux out of the S1 plus S2 plus S3, so literally you should do what? S1 plus S2 plus S3, right? Plus S3. Pardon me? Not necessary. Not necessary. Yeah. They're literally 2 different surfaces, right? Yeah. You could be 0, but that doesn't mean they're cancel out. Yeah. So you will do this, right? You will do this. Now tell me. So we're in this question here. This is a question S1 equal to what, right? In this part we're doing S1. But if you really do S1 plus S2 plus S3, for S2, right? For S2, what's your n hat? I don't want you to get everything. What's your n hat for S2? K. For S3, what's your n hat? Negative K. Very good, right? That's the orientation we're talking about here, okay? Yeah. And you can fill out the other missing informations for the calculation, but yeah. Cancel out. See, okay, let's see, right? If you have an enclosed surface like this, okay, yeah, and you calculate. This is one piece of surface. You calculate our surface. You get a number, right? Now, same thing. You calculate inward surface. Guess what? These two must be not equal. Must be opposite each other, right? Now you add these two, they cancel out. But this is the difference, This is calculating our surface, which consists of S1 plus S2 plus S3. There's actually no cancellation at here. There's no concept cancellation at here. Huh? Yeah. Yeah.
There would be cancellation if the field was all the same everywhere. But in this case,
symmetric. You're talking about
EMAG. I think that's what everyone's getting confused about. Because in EMAG we had the same field everywhere.
Okay.
Which would mean the top and bottom would cancel out because
we're
going through the same amount of area.
Yeah.
And it's just the normal vector.
Very good point. Yeah. If you have a constant field, right? You've got a constant field, maybe all pointing outwards, everywhere constant. Of course, the upward flux to S2 compared to downward flux S3, they cancel out each other, right? Yeah. Okay. Yeah. There is another one. I don't want to confuse. Anyway, so in the next couple of there's another situation you'll see that. Okay. Yeah. So, but for now, in terms of calculating the flux for enclosed surface, so you got to look at how many pieces of surface there, right? Then you add the flux out of each one of the surface accordingly with the proper orientation, okay? And then you'll get the total flux out of the surface. Okay. So in this question, as we said, we're basically calculating S1 in here, right? Okay. And n hat, okay, as we said, okay, for a cylindrical surface, and here the cylinder has a radius of a equal to 1, so that's just x, y, 0 now. You're going to replace the x with cosine theta, y with sine theta, and the z will be kept the same, okay, as z. Now, you should have an r at here, you should have an a at here, but a is 1, right? So that's why just cosine theta, sine theta. And dA, right, is a dz d theta. and a equal to 1, so it will just be dz d theta. Okay, so you got everything here. Let's put it into this question. So this is a cylinder, huh? Maybe I want to be more specific. So F is x, z, negative y. That's your vector field. And n hat is x, y, 0. And dA is dz, d theta. Okay. So multiply this dot product out. X squared plus zy, and then dz, d theta. And this is still the same surface. Okay. And now we're going to do the replacement. We replace the x with cosine theta. Replace the z with the z, and replace the y with sine theta. Okay, because a equal to 1. And then dz, d theta. Okay. And last step, figure out the limits for z and the theta. So this is the cylinder. Finding the z is basically you draw arrow lines in the z-axis direction. First contact, second contact, give you z min, z max. So that's 0 to 1. And theta depends on the shadow. This is the whole cylinder, so it will be 0 to 2 pi. Right. So that's the limit. Okay. And the rest of the work is just simple integrals to finish this whole thing. Okay. Yeah. So you can try it out. There is a little bit of trig identity involved for this question, but you're going to get a number that equal to pi. Okay. So I want you to exercise, okay, basically yourself. What if we really just includes the top and the bottom surface? Okay, yeah. And then what will be the total for our flux now? Okay, so try it out. We'll finish the next case in the next lecture. Okay, thank you. We do have a number 8 due next week. Now I have a number 9, which is a self-study assignments. Basically, it has something to do with the last 2 lectures for the next week. Okay. Unfortunately, you have a very short time after the last lecture, so it means you have a very short amount of time to prepare. You do need to prepare for all the assignments, though. I will post everything. Everything will be up on the Connect. Okay. That'll be all of your preparation material.